Now we're going to see the distribution of charges. It could be for a weird shaped conductor, so it is not a spherical conductor like this as we have been talking. Now we are talking about a, let's say, this conductor. So we will see that there is greater density, surface density, at the points in which the radius of curvature is greater. So when radius of curvature is greater. Here we have the greatest radius of curvature, and in all this we have the smallest one. So why is this? It is because, before coming to this, let me put it as this. They are communicated, and they have the same potential. We know that the potential is the negative of 1 over 4 p epsilon naught times r and times q. So for this, let's say that this ball is ball B and this is ball A. So the voltage of B is equal to the voltage of A. So voltage of B is Q of B divided by 4 p epsilon naught r sub B, and this is equal to Q sub A divided by 4 p epsilon naught RA. Let's say that the radius of B is 5 times the radius of A. That means that, because here I can cancel all these, I have that QB over RB is equal to QI over RA. So if R sub B is 5 times R sub A, so here I could put 5 RA, I need that QB, I need to put here 5 QA in order to cancel the 5 and so get that QA over RA is QI over RA. So that means that I would have higher number of charges here when the radius is greater than here when the radius of curvature is less. How much would it be? Well, I have the density, the charge density or the charge surface density is just the charge over the area. Here, the density at this point versus the density at this point, or whatever. Here, I have the density at this point would be Q sub B over area sub A, and here would be Q sub A over area sub A. Here the charge is 5A, 5QA, and the area is 4B R squared. R is 5R, so this would be 25R sub A, and this versus Q sub A divided by 4B R sub A square. So if I want to know how many times more charge density I have here than here, or here than here, when I have the greater radius of curvature, that would be just 1 over 5. Sorry, 1 over 5 is how many times more charge density I have in B than in A, because I divided this by this. or the other way around, if you want to divide this by this, then you would have 5 instead of 1 over 5. So this was one of the distributions that I wanted to talk about. In other videos we will talk more specifically about conductors and insulators. In conductors the charges are on the surface, and in insulators they are on all the sphere or object that we have. Just something to mention is you have here a conductor. By Gauss law, the electric field is 0 inside. If I put a positive charge here, I would induce negative charges here. But still, the electric field inside would be 0 because now all these will add the same quantity as this. In order to do that, I also induced positive charges here. If I move this in the inner part, it doesn't affect anything, but it doesn't affect anything in relation to the electric field, but to the distribution of charges, yes, because if I put Q closer here, then I will have a higher density of negative charges here, and then less and less and less. But the distribution of the positive charges that are induced over the surface of the sphere, this would remain the same here. The distribution of positive charges outside the sphere is the distribution is the same as compared to here, in which the distribution of the negative charges is different.